Are we ever going to leave the Milky Way? This question touches on one of the most profound challenges humanity could ever face, and the answer reveals something extraordinary about the nature of our universe and our place within it. To truly understand whether we might one day venture beyond our galactic home, we need to explore some of the most fascinating and rarely discussed aspects of intergalactic travel, the bizarre physics that govern the cosmos, and the ultimate fate awaiting our island of stars. The first thing to understand is that leaving the Milky Way is not simply a scaled-up version of leaving Earth, or even leaving our solar system. The distances involved are so incomprehensibly vast that they fundamentally change the nature of the problem. Our galaxy stretches approximately 100,000 light-years from edge to edge, and the nearest major galaxy to us, Andromeda, lies roughly 2.5 million light-years away. To put this in perspective, if you could travel at the speed of light itself, which is roughly 186,000 miles per second, it would still take you 2.5 million years to reach Andromeda. This is not merely a technological challenge, it is a confrontation with the very structure of spacetime itself. One of the most intriguing and seldom discussed aspects of intergalactic travel involves something called the cosmological horizon. As our universe expands, and that expansion is actually accelerating due to dark energy, distant galaxies are moving away from us at ever-increasing speeds. There exists a boundary beyond which galaxies are receding from us faster than the speed of light. This does not violate relativity because the galaxies themselves are not moving through space faster than light. Rather, the space between us and those galaxies is expanding at such a rate that the distance grows faster than light could traverse it. This means that there are galaxies we can see today whose light has reached us, but which we could never reach, even if we could travel at the speed of light, because they are already beyond our cosmological horizon. In fact, the number of galaxies we could theoretically reach is constantly shrinking as the universe's expansion accelerates. Current estimates suggest that only about 3% of the galaxies we can observe today will remain reachable if we wait too long. Every moment we delay, more galaxies slip beyond our reach forever, carried away by the expanding fabric of space itself. This creates a peculiar urgency to the question of intergalactic travel. If humanity or its descendants ever wish to explore beyond the Milky Way, there is quite literally a cosmic clock ticking. Wait too long, and the universe becomes an increasingly lonely place, with fewer and fewer islands of matter accessible to us. But there is a twist to this story that offers a strange form of hope. In approximately 4.5 billion years, our Milky Way galaxy is going to collide with the Andromeda galaxy. This is not a sudden, violent crash in the way we might imagine a car accident. Galaxies are mostly empty space, and when they merge, the individual stars rarely collide with one another. Instead, their gravitational fields intermingle, and the galaxies slowly blend together over hundreds of millions of years, creating a new, larger galaxy that astronomers have playfully nicknamed Milkomeda or Milkdromeda. This collision means that, in a sense, the question of whether we will leave the Milky Way becomes moot. The Milky Way, as we know it, will cease to exist as a distinct entity, merged into something larger. Any civilization that survives until that time will find itself residing in a galaxy that already contains what was once the nearest major intergalactic destination. This galactic merger also highlights an important point about the nature of cosmic timescales. 4.5 billion years is roughly the same amount of time that has elapsed since Earth first formed. The entire history of our planet, from the formation of the first oceans to the emergence of life, the reign of the dinosaurs, and the eventual evolution of humans, All of that fits into a span of time equal to how long we have until this collision begins. When we talk about intergalactic travel and the future of humanity, we are necessarily talking about timescales that dwarf all of human history thousands of times over. Now, let us consider the actual physics of traveling between galaxies. The fastest spacecraft ever built by humans is the Parker Solar Probe, which has reached speeds of approximately 430,000 miles per hour relative to the Sun. This sounds impressively fast, and it is by human standards. But at this speed, it would take this probe about 6,000 years just to reach the nearest star to our Sun, Proxima Centauri, which is only about 4 light-years away. To reach Andromeda at this speed would require roughly 6 billion years, which is longer than the current age of the Earth, and longer than the time remaining before our Sun exhausts its hydrogen fuel and begins to die. Clearly, conventional propulsion is not going to get us to another galaxy. We need to consider more exotic possibilities. One concept that physicists have explored is the Alcubierre drive, named after physicist Miguel Alcubierre, who proposed it in 1994. This theoretical propulsion system would not move a spacecraft through space in the conventional sense. Instead, it would contract space in front of the spacecraft and expand space behind it, creating a bubble of warped spacetime that carries the ship along. Inside this bubble, the spacecraft and its occupants would experience no acceleration and could theoretically remain in an inertial reference frame, experiencing normal time and avoiding the time dilation effects of special relativity. The beautiful thing about the Alcubierre drive is that it does not violate the laws of physics as we understand them. General relativity permits this kind of space-time manipulation. However, and this is a significant however, the energy requirements are staggering beyond comprehension. Early calculations suggested that creating such a warp bubble would require an amount of negative energy equivalent to the total mass energy of Jupiter. Negative energy is itself a problematic concept, related to exotic matter with negative mass, which has never been observed and may not exist at all. Later refinements of the concept have reduced the energy requirements somewhat, but we are still talking about energy scales that dwarf anything humanity has ever harnessed. We would need to manipulate the fundamental fabric of space-time itself, something that currently exists only in mathematical equations and science fiction. Another proposed method for extreme space travel involves the concept of a generation ship, sometimes called a world ship. This is a massive spacecraft designed to support a human population for thousands or even millions of years as it slowly crosses the cosmic void. The ship would need to be entirely self-sufficient, with closed-loop life support systems that recycle everything perfectly. It would need to protect its inhabitants from cosmic radiation, provide artificial gravity to prevent the health problems associated with long-term weightlessness, and maintain a stable society across countless generations who would be born, live, and die aboard the vessel, never knowing any other home. The psychological and sociological challenges of such a mission are profound and rarely discussed in detail. How do you maintain a sense of purpose across 100 generations or more? The people who arrive at the destination galaxy would be so far removed from those who launched the mission that they would share no cultural memory, no direct connection beyond DNA, and perhaps some preserved records. Every language evolves, cultures shift, and values change. The society that arrives might bear little resemblance to the one that departed. There is also the question of genetic diversity. A generation ship would need to maintain a large enough population to avoid inbreeding and genetic drift, which some scientists estimate would require at least several thousand individuals, though estimates vary widely. Managing such a population's genetic health over geological timescales presents challenges we have never faced. Some researchers have proposed that advanced civilizations might use suspended animation or cryogenic freezing to preserve travelers during long voyages. This would solve many of the generation ship problems, as the same individuals who departed would arrive at the destination. However, we currently have no technology that can safely freeze and revive a human being. The formation of ice crystals during freezing ruptures cell membranes and destroys tissue. Some organisms, like certain frogs and insects, have evolved biological antifreeze compounds that prevent ice crystal formation. But scaling this up to preserve something as complex as a human brain, with all its intricate neural connections intact, remains firmly in the realm of speculation. There is also the concept of uploading human consciousness into computer systems and sending only the digital information across space. A spacecraft carrying computer servers would be far lighter than one carrying biological humans with all their life support needs. If we could somehow capture everything that makes a person who they are, their memories, personality, consciousness, and encode it digitally, then that information could theoretically travel at close to the speed of light via laser or radio transmission. Upon arrival, the consciousness could be downloaded into a new body, perhaps biological, perhaps robotic. This concept faces both technical and philosophical challenges. We do not currently understand consciousness well enough to know if it can be uploaded, and there are deep questions about whether a digital copy would truly be you or merely a replica that thinks it is you. If I make a perfect copy of you and then destroy the original, has the original you survived or died? These are not just academic questions. They strike at the heart of identity and what it means to be human. Beyond these somewhat conventional, if highly speculative approaches, there are even more exotic possibilities that push the boundaries of known physics. Some theoretical physicists have explored the concept of traversable wormholes, shortcuts through spacetime that could connect two distant points in the universe. If such structures could exist, and if they could be stabilized, perhaps using exotic matter with negative energy density, they might allow near-instantaneous travel across cosmic distances. However, most physicists believe that even if wormholes can exist, they would be incredibly unstable and would collapse before anything could pass through them. The energy required to create and stabilize a wormhole, large enough for a spacecraft, or even just information to pass through, would likely be comparable to or exceed the energy output of entire stars. Another rarely discussed possibility involves taking advantage of future astronomical events. As mentioned earlier, the Milky Way and Andromeda are going to merge. During this merger, which will take place over hundreds of millions of years, stars from both galaxies will be scattered into new orbits. Some stars will be flung out of the resulting merged galaxy entirely, ejected by the complex gravitational interactions. If humanity or its descendants could position themselves on a planetary system that gets ejected during this merger, they would find themselves on an intergalactic journey not of their own making. They would be passengers on a natural spacecraft, a star system sailing through the void between galaxies. This journey would be slow, potentially taking billions of years to reach another galaxy, if indeed they ever did. But it would require no fuel, no exotic physics, merely patience on a cosmic scale. This brings us to one of the fundamental questions underlying all discussions of intergalactic travel. Will anything recognizable as humanity still exist on these timescales? 4.5 billion years from now, when the Milky Way and Andromeda collide, it is almost inconceivable that biological humans, as we know them, will still exist in an unchanged form. Evolution operates constantly, and even if we do not actively modify ourselves through genetic engineering or merge with technology, we will continue to evolve. The humans of the far future, if they exist at all, may be as different from us as we are from the small, shrew-like mammals that scurried between the feet of dinosaurs. They might be digital consciousnesses living in vast computer networks, or they might be beings of pure energy, or they might have transformed into something we cannot even imagine with our current biological brains. This touches on a concept sometimes called the post-biological universe. Many scientists and futurists speculate that biological intelligence is merely a brief phase in the evolution of intelligence in the universe. Just as single-celled organisms gave rise to multicellular life, and simple nervous systems gave rise to complex brains, biological brains may give rise to artificial intelligences that far surpass us. These artificial intelligences would not face the same limitations we do. They would not need oxygen, water, or food. They could potentially survive the vacuum of space, extreme temperatures, and intense radiation. They could be backed up and copied, making them effectively immortal. For such beings, the journey between galaxies, though long, might not seem as daunting as it does to us. They could simply put themselves into a low-power mode and wait out the journey. Or they could operate on timescales we cannot comprehend, thinking thoughts that take centuries to complete, but processing information far more deeply than we ever could. There is also the Fermi paradox to consider. This is the apparent contradiction between the high probability of extraterrestrial life existing and the complete lack of evidence for it. If intelligent life is common in the universe, and if it has existed for billions of years in many places, where is everyone? One possible answer, known as the Great Filter, suggests that there is some barrier that prevents civilizations from reaching the stage where they can engage in intergalactic travel or even interstellar communication. This filter might be behind us. Perhaps the jump from non-life to life is incredibly rare. Or it might be ahead of us, some inevitable catastrophe that befalls all technological civilizations before they can spread beyond their home planet or solar system. If the Great Filter is ahead of us, then our discussions of intergalactic travel might be moot because we might not survive long enough to attempt it. However, there is another interpretation of the Fermi paradox that relates directly to our question. Perhaps intergalactic travel is simply so difficult, so beyond the reach of any civilization, that no one does it. Interstellar travel within a galaxy is already monumentally challenging, but at least the distances are somewhat manageable. Stars within a galaxy are typically separated by a few light years, but galaxies are separated by millions of light years. Perhaps this is a natural boundary, a limit set by physics itself that keeps civilizations confined to their home galaxies. In this view, galaxies might be thought of as isolated islands in a vast ocean of space, each potentially hosting many civilizations, but with no way for those civilizations to ever meet. Let us examine more closely what happens to spacecraft as they attempt to reach extreme velocities. At speeds approaching the speed of light, several strange effects predicted by Einstein's theory of special relativity become important. One is time dilation. For travelers moving at relativistic speeds, time passes more slowly than it does for stationary observers. If you could build a spacecraft that could accelerate to 99.9% of the speed of light, for the travelers aboard that ship, the journey to Andromeda might seem to take only tens of thousands of years subjectively, even though millions of years would pass on Earth. At speeds even closer to light speed, this effect becomes more pronounced. At 99.9999% of the speed of light, The journey might feel like only a few decades to the travelers, though 2.5 million years would elapse in the outside universe. This time, dilation offers a strange loophole. In principle, you could travel anywhere in the visible universe within a human lifetime, subjectively, if you could get close enough to the speed of light. However, you could never return home to the time you left. You would arrive at your destination to find that everyone you knew was dead, that entire civilizations had risen and fallen, that the stars themselves had changed. You would be a time traveler into the future with no way back. This one-way nature of relativistic travel creates profound psychological and social challenges. Would anyone volunteer for such a mission, knowing they would be abandoning their entire world permanently? There is also the problem of the interstellar medium. Space is not truly empty. There are gas atoms, dust particles, and cosmic rays scattered throughout space. At low speeds, these pose little problem. But at relativistic velocities, even individual hydrogen atoms become deadly projectiles. At 99% of the speed of light, a collision with a single hydrogen atom would release energy equivalent to hundreds of nuclear bombs. A spacecraft traveling at such speeds would need extraordinary shielding to survive passage through even the very tenuous interstellar medium, let alone the intergalactic medium. The shielding itself would add mass to the spacecraft, which would require more energy to accelerate, creating a vicious cycle. Some proposed solutions include using powerful magnetic fields to deflect charged particles, or deploying a disposable shield ahead of the spacecraft that would absorb impacts. Another concept involves using a laser to clear a path through space ahead of the ship, ionizing atoms so they can be deflected magnetically. All of these solutions require massive amounts of energy and sophisticated technology we do not currently possess. The energy requirements for relativistic travel are truly staggering. To accelerate even a small spacecraft to a significant fraction of the speed of light requires energy measured in terms of entire planets' worth of resources. Various propulsion concepts have been proposed to address this. One is the Bussard ramjet, conceived by physicist Robert Bussard in 1960. This theoretical engine would use a powerful magnetic field to scoop up hydrogen from the interstellar medium and use it as fuel for a fusion reactor. The beauty of this concept is that the spacecraft would not need to carry all its fuel with it. It would gather fuel as it goes, like a jet engine scooping air. However, the engineering challenges are immense. The magnetic scoop would need to be enormous, potentially thousands of kilometers across, and we still have not achieved sustained, controlled fusion reactions that produce more energy than they consume. Another concept is the laser sail or photon sail. This involves a large, extremely thin reflective sail, potentially kilometers across, pushed by powerful lasers based back at the origin point. The advantage is that the spacecraft itself needs no fuel or engine. The disadvantage is that the laser installation would need to be phenomenally powerful, capable of delivering petawatts or even exawatts of power, focused into a tight beam across interstellar distances. Building such an installation would be a massive undertaking, likely requiring resources on the scale of entire planets. Also, once the spacecraft reaches cruising speed, there is no way to slow down unless there is another laser installation at the destination, which presents a chicken-and-egg problem for the first mission. Matter-antimatter annihilation represents perhaps the most energy-dense fuel source permitted by physics. When matter meets antimatter, they annihilate completely, converting 100% of their mass into energy, according to Einstein's famous equation, E equals mc squared. No other reaction is this efficient. Conventional chemical rockets convert only about 1/1000th of their fuel's mass into useful energy. Nuclear fusion converts about 1%. Matter-antimatter annihilation converts it all. A spacecraft powered by matter-antimatter reactions could theoretically achieve a significant fraction of light speed. The problems are that we can only produce antimatter in tiny quantities at enormous expense, and storing it safely is incredibly difficult because if it touches any normal matter, it annihilates. We would need to confine it using magnetic fields or keep it at extremely low temperatures, and even a small containment failure would result in a catastrophic explosion. As we contemplate these vast challenges, it is worth considering what we would find if we did manage to reach another galaxy. The universe is about 13.8 billion years old. Galaxies formed relatively early in cosmic history, and the physical laws are the same throughout the universe. This means that other galaxies should contain stars and planets, much like those in our own galaxy. Some of those planets likely harbor life, and some of that life has probably evolved intelligence. When we look at Andromeda, we are seeing light that left that galaxy 2.5 million years ago. If there are civilizations there, they might be looking back at the Milky Way, seeing it as it was 2.5 million years ago. Any communication between galaxies would face this same enormous time delay. A conversation would take 5 million years for a single exchange of messages. This time delay has interesting implications for what intergalactic travel might be like. By the time we could receive a signal from another galaxy and respond, entire eras of history would have passed. Imagine if the Roman Empire had sent a message to another galaxy. The response would only just now be arriving, addressed to a civilization that has not existed for over 1,000 years, written in languages long dead. Any information in that response would be 2.5 million years out of date by the time we received it. The galaxy we finally reached would be vastly different from the one we studied before launching our mission. Stars would have been born and died. Planets would have formed and been destroyed. Civilizations might have risen to heights we cannot imagine and fallen to dust. The energy available to a civilization provides a useful framework for thinking about what might be possible for advanced civilizations. Astronomer Nikolai Kardashev proposed a scale in 1964 that classifies civilizations by their energy use. A Type 1 civilization can harness all the energy available on its home planet. A Type 2 civilization can harness the total energy output of its star, perhaps by building a Dyson sphere, a megastructure that surrounds the star and captures most or all of its light. A Type 3 civilization can harness the energy of an entire galaxy, potentially utilizing the output of billions of stars. Humanity currently ranks at about 0.7 on this scale. We use only a fraction of the energy available on Earth. Reaching Type 2 status would require us to build structures on a scale we can barely imagine. A Dyson sphere around our sun would require disassembling multiple planets to gather enough material. The engineering challenges of building a structure hundreds of millions of kilometers across that can withstand the sun's radiation and maintain structural integrity are beyond anything we have attempted. Yet, such a structure would provide energy on a scale that makes interstellar travel far more feasible. With the full output of a star at our disposal, the energy requirements for relativistic spacecraft become more manageable. A Type 3 civilization, one that has somehow harnessed the power of an entire galaxy, would have resources we cannot comprehend. Such a civilization might be capable of projects like creating artificial wormholes, manipulating spacetime on galactic scales, or perhaps even creating new universes. If such civilizations exist in other galaxies, they might already have solved the problems of intergalactic travel. Indeed, they might have visited us, though we might not recognize their technology for what it is. Arthur C. Clarke famously said that any sufficiently advanced technology is indistinguishable from magic. A truly advanced civilization's technology might be indistinguishable from natural phenomena. This leads to some fascinating speculation. What if some of the things we observe in the universe are actually the work of advanced civilizations? Could gamma-ray bursts, the most energetic events we observe in the universe, possibly be the byproducts of some inconceivable technology? Could the apparent accelerating expansion of the universe be influenced by civilizations we cannot detect? These ideas are highly speculative, but they illustrate how little we truly understand about what might be possible. There is also the question of why we would want to leave the Milky Way in the first place. What drives the impulse to explore? For early humans, exploration was often driven by necessity, the search for food, water, or safer territory. Later, it was driven by curiosity, trade, or conquest. In space, there are no resources that cannot be found closer to home. Anything you might find in another galaxy surely exists somewhere in our own Milky Way, which contains hundreds of billions of stars. The scientific knowledge gained from visiting another galaxy might be interesting, but we can learn most of what we need to know by observing with telescopes. The energy and resources required for an intergalactic mission could surely be better spent on other projects. Perhaps the real reason for attempting such a journey would be more abstract. The simple fact that it is there, and we can do it, or the desire to ensure the survival of human or post-human intelligence against some future catastrophe. Even galaxies are not eternal. Stars eventually exhaust their fuel. Our sun will become a red giant in about 5 billion years, expanding to engulf the inner planets, likely including Earth. Eventually, all stars will die. In the far future, measured in trillions of years, the universe will become a cold, dark place, where stars no longer form because all the available hydrogen has been used up. Existing stars will burn out one by one, until only black holes and cold remnants remain. This era, sometimes called the degenerate era, will last far longer than the current stelliferous era, where stars shine. Even black holes eventually evaporate through a process called Hawking radiation, though this takes an incomprehensibly long time, on the order of 10 to the 100th power years for large black holes. After all the black holes have evaporated, the universe enters what is called the dark era, where all that remains is an increasingly dilute sea of elementary particles spreading ever farther apart as space continues to expand. In such a universe, life as we know it cannot exist. The energy sources that life depends on, whether the light of stars or the heat of planetary cores, will all have gone cold. Some physicists have speculated about whether intelligence could potentially survive even these conditions by slowing down its thought processes to match the available energy. Taking advantage of the decreasing temperature of the universe to run computations more efficiently, or even downloading into the fabric of spacetime itself. These ideas are extraordinarily speculative and rely on physics we do not yet understand. But they illustrate that thinking about the far future of intelligence in the universe necessarily involves thinking on timescales that make even intergalactic travel seem trivial. In the shorter term, measured in mere billions of years rather than trillions, there are other motivations for spreading beyond the Milky Way. Catastrophes that could threaten an entire galaxy, while rare, are not impossible. A supernova, the explosion of a massive star, can release more energy in a few seconds than our sun will emit in its entire lifetime. These explosions can sterilize planets within hundreds of light years. Even more energetic are gamma-ray bursts, which can affect regions thousands of light years across. a sufficiently close gamma-ray burst could potentially threaten all life in a significant portion of a galaxy. By spreading to multiple galaxies, intelligence could ensure that no single catastrophe could eliminate it entirely. There is also the possibility of more exotic threats. Some theories suggest that the vacuum of space might not be in its lowest energy state, a true vacuum, but rather in a false vacuum, a metastable state that could suddenly decay to a lower energy state. If this happened, a bubble of true vacuum would expand at the speed of light, fundamentally altering the laws of physics in the affected region. Atoms, as we know them, could not exist within this bubble. Such a vacuum decay event could sterilize an entire region of space, potentially even spreading across the entire universe. Being in multiple galaxies would not protect against this particular threat, but it illustrates the kinds of existential risks that motivate thinking about the long-term survival and spread of intelligence. Let us return to the more immediate question of whether we, meaning current humans, or our near-term descendants, will ever leave the Milky Way. The answer is almost certainly no, at least not in the sense of biological humans traveling to another galaxy within any recognizable future. The distances are too vast, the energy requirements too extreme, and the time scales too long. Our current technology is not even close to what would be needed. We have barely begun to explore our own solar system. The furthest human-made objects, the Voyager probes, launched in 1977, have only recently entered interstellar space after more than 40 years of travel. They are about 22 billion kilometers from Earth, which sounds impressive until you realize that this is only about 0.2% of 1 light year. They would need to travel for another 20,000 years to reach even the nearest star. However, the question becomes more interesting when we consider longer timescales and the possibility of post-biological intelligence. If humanity can avoid extinction, if we can navigate the challenges of climate change, nuclear weapons, pandemics, artificial intelligence alignment, and the countless other risks we face, then we have a long future ahead of us. Our sun will shine for another 5 billion years. Even if biological humans do not survive in their current form, our descendants, whether biological, digital, or something in between, will have billions of years to develop technologies we cannot imagine. On these timescales, what seems impossible today might become routine. Consider that only a little over 100 years ago, humans first achieved powered flight. Only 66 years later, we landed on the moon. The exponential pace of technological development, at least in recent centuries, suggests that extrapolating current limitations far into the future is unwise. Technologies that seem to violate the laws of physics today might turn out to be possible through principles we have not yet discovered. Physics is not complete. We know this because quantum mechanics and general relativity, our two most fundamental theories, are incompatible with each other in certain regimes. We do not have a working theory of quantum gravity. We do not understand what dark matter or dark energy are, yet they make up 95% of the universe. There is clearly much we do not know. Future discoveries might reveal new physics that makes intergalactic travel feasible. Perhaps there are shortcuts through spacetime we have not imagined. Perhaps the speed of light is not truly a universal speed limit in all circumstances. Perhaps consciousness can be transmitted in ways we do not currently understand. We should be humble about declaring what is forever impossible when our understanding of the universe is clearly incomplete. There is also the possibility that we are not the first intelligent species in the Milky Way or in the universe. If other civilizations exist, and some of them are older than us, they may have already solved these problems. They might have left behind artifacts or technology we could discover. Some scientists seriously search for these kinds of technosignatures, evidence of advanced technology operating on astronomical scales. So far, we have found nothing, but we have only just begun to look, and we would only recognize technology that we know to look for. When we think about the Milky Way itself, it is worth appreciating what a remarkable place it is. Our galaxy contains somewhere between 100 billion and 400 billion stars, and current estimates suggest that most of these stars have planets. Many of these planets are in the habitable zone of their stars, where liquid water could exist on the surface. The sheer number of potentially habitable worlds in our galaxy is staggering, likely in the billions. Each of these worlds is a place where life might have emerged, where evolution might have produced intelligence, where civilizations might have risen and perhaps fallen. Our galaxy is a barred spiral galaxy, meaning it has a bar-shaped structure of stars across its center, with spiral arms extending outward. We live in a relatively quiet neighborhood, about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Arm, or local spur. This is actually a very fortunate location. The galactic center is a chaotic place with a supermassive black hole, weighing about 4 million times as much as our Sun, surrounded by densely packed stars and intense radiation. Planets in the galactic core would be subject to frequent gravitational perturbations and radiation that might make complex life difficult or impossible. Out here in the suburbs, stars are more widely spaced, orbits are more stable, and conditions are calmer. This might be one of the reasons life was able to develop on Earth. The Milky Way is also part of a larger structure called the Local Group, a collection of about 80 galaxies bound together by gravity. Besides the Milky Way and Andromeda, which are the two largest members, the Local Group contains the Triangulum Galaxy and dozens of smaller dwarf galaxies. These galaxies orbit around each other in a slow cosmic dance. Eventually, over billions of years, many of them will merge together. The Local Group itself is part of an even larger structure called the Virgo supercluster, which contains thousands of galaxies. And the Virgo supercluster is part of the Laniakea supercluster, which contains about 100,000 galaxies. These hierarchical structures remind us that galaxies are not isolated islands, but part of a cosmic web of matter stretching across the universe. This large-scale structure was seeded by tiny quantum fluctuations in the very early universe, just after the Big Bang. Those fluctuations grew over billions of years, pulled together by gravity, eventually forming the galaxies and clusters we see today. When we look at the distribution of galaxies across the universe, we are seeing the echo of processes that occurred when the universe was less than a second old. One of the most profound realizations of modern cosmology is that we live in a universe that had a beginning and will have an end, at least in any form that would support complexity. The Big Bang happened approximately 13.8 billion years ago. Before that, we cannot say what existed because our physics breaks down at the extreme temperatures and densities of the earliest moments. Perhaps there was nothing. Perhaps there was something else, another universe or a different phase of space-time. We do not know. What we do know is that the universe has been expanding ever since, and that expansion is accelerating. This acceleration was discovered in the late 1990s by observing distant supernova and was completely unexpected. Something, which we call dark energy for lack of a better name, is pushing space apart. We do not know what dark energy is. It might be a property of space itself, a cosmological constant as Einstein once proposed and then retracted. It might be a dynamic field that changes over time. The implications of dark energy for the far future are profound. If it continues to accelerate the expansion, then eventually all galaxies beyond our local group will recede beyond our cosmological horizon. The universe will become increasingly empty from our perspective, even though it might be full of galaxies we simply cannot see or reach. In the very far future, trillions of years from now, an observer in the merged Milky Way Andromeda galaxy would look out at a universe that appears almost empty. The cosmic microwave background radiation, the echo of the Big Bang that currently fills the universe with faint microwave light, will have been redshifted to invisibility. There will be no evidence of the Big Bang, no evidence that the universe extends beyond the local group. Such observers, if they existed, and if they developed science, would come to very different conclusions about the nature of the universe than we do. They would have no way to know about the billions of galaxies that once filled the cosmos. This is a humbling thought. It suggests that there might be aspects of the universe that are currently invisible to us, evidence of processes or structures that have already passed beyond our cosmological horizon. Thinking about these vast timescales and cosmic structures can feel overwhelming. It is difficult for human minds, evolved to deal with human-scale problems on human timescales, to truly grasp billions of years or millions of light years. We understand these concepts intellectually, but they do not feel real in the same way that our immediate surroundings do. Perhaps this is why the question of whether we will ever leave the Milky Way feels somehow both urgent and pointless. Urgent because every moment we delay, more of the universe becomes unreachable. Pointless because the scales involved are so beyond human experience that they feel abstract. Yet, there is something profound about asking the question. It forces us to confront our place in the cosmos, to recognize both how small and how special we are. We are small because we occupy a tiny planet orbiting an ordinary star in an unremarkable galaxy among billions of galaxies. We have existed for only a cosmic instant and will likely disappear without leaving a trace visible from beyond our solar system. But we are special because, as far as we know, we are the only beings in the observable universe who can ask these questions, who can wonder about the nature of reality and our place within it. The fact that the universe has produced beings capable of understanding it, at least partially, is perhaps the most remarkable fact of all. The atoms in our bodies were forged in the cores of stars that exploded billions of years ago. We are, quite literally, made of stardust. The universe has become aware of itself through us. This self-awareness is rare and precious, perhaps unique in all the cosmos, though we do not know for certain. If we do someday venture beyond the Milky Way, it will not be driven by practical necessity, but by this sense of wonder and curiosity, by the desire to know what is out there and to push the boundaries of what is possible. The journey itself might be as important as the destination. The knowledge gained, the technologies developed, the transformations undergone in the attempt to reach other galaxies might fundamentally change what we are and what we can become. Consider the possibility of a spacecraft that takes millions of years to reach another galaxy. The beings who arrive would have evolved during the journey. The ship itself would be their world, their entire universe for thousands of generations. They would develop their own culture, their own relationship with the cosmos. By the time they arrived, they might have forgotten Earth entirely, or it might have become a mythical place, the subject of stories and legends, but not a real, living memory. The mission would have transformed them into something new, something that has never existed before, a species shaped by the cosmos itself. Or perhaps the journey would not involve physical travel at all. Perhaps we will learn to encode ourselves as information and transmit that information using lasers or radio waves. The information could travel at the speed of light, arriving at another galaxy in millions of years rather than billions. Upon arrival, it could be used to reconstruct us, either in biological form, if the destination has the necessary materials and technology, or in digital form within computer systems. This raises fascinating questions about identity and continuity. Is the reconstructed being really you, or is it a copy? Does it matter? If your pattern, your memories, your personality are preserved, is that sufficient for survival? Some philosophers argue that identity is not about physical continuity, but about psychological continuity. You are not the same collection of atoms you were 7 years ago. Your cells have been replaced many times over, yet you consider yourself the same person. What makes you you is the continuity of your memories and personality, not the specific atoms that make up your body. If this is true, then perhaps transmission and reconstruction is a form of survival after all. But others argue that there is something special about physical continuity, about the unbroken stream of consciousness. Breaking that stream, even if a perfect copy is created elsewhere, might be a form of death for the original. These philosophical questions are not merely academic when we talk about intergalactic travel. They become practical issues that would need to be resolved before anyone would volunteer for such a mission. Would you step into a machine that scans your brain in perfect detail, encodes that information, and then transmits it to another galaxy, knowing that a copy of you will wake up there millions of years later, but also knowing that you, the original, might be destroyed in the scanning process? This is not so different from the question of whether you would use a Star Trek transporter, which supposedly disassembles you at one location and reassembles you at another. Many people find this idea disturbing, even though it is functionally indistinguishable from what happens to us naturally over longer timescales, as our atoms are gradually replaced. The Milky Way galaxy is about 10 billion years old, making it roughly 3/4 the age of the universe itself. It formed from the gradual accumulation of gas and dark matter, with early generations of stars being born, living their lives, and exploding, enriching the interstellar medium with heavier elements. Our Sun is a third-generation star, meaning it formed from material that had already been processed through earlier stars. This is why Earth contains elements heavier than helium. The first stars in the universe, population 3 stars as astronomers call them, contained only hydrogen and helium because those were the only elements created in the Big Bang. They could not have had planets like Earth because there were no heavier elements to make rocky planets from. Life as we know it would have been impossible around those first stars. It took billions of years for the universe to create the conditions necessary for planets like Earth and life like us. We are the inheritors of that long cosmic history. When we look up at the night sky, we see light that has traveled for years, centuries, or even millions of years to reach our eyes. We are looking into the past, seeing the universe as it was, not as it is. This time, delay becomes more extreme as we look at more distant objects. When we observe Andromeda, we see it as it was 2.5 million years ago. Any civilizations there are seeing the Milky Way as it was 2.5 million years ago. We are looking at each other's past, never the present. This temporal displacement has interesting implications for what intergalactic contact might be like. Imagine we detect a signal from another galaxy that contains a message from an intelligent civilization. That civilization existed at least millions of years ago when they sent the message. They might still exist now, or they might have gone extinct long ago. There is no way to know. If we send a response, it will take millions of years to arrive, and then millions more years for their reply to reach us. Any exchange of information happens on geological timescales. You cannot have a conversation. You can only send messages into the future, hoping someone will be there to receive them. This might actually make intergalactic communication more appealing than intergalactic travel in some ways. Sending information is much easier than sending physical objects. We could broadcast everything about ourselves, our history, our knowledge, our culture, encoded in radio waves or laser beams, aimed at other galaxies. This information would travel at the speed of light, arriving millions of years later. If anyone is listening, they would receive a complete record of our civilization as it existed at the moment we transmitted. We could achieve a kind of immortality, our culture preserved even if we ourselves go extinct. Other civilizations could do the same, filling the universe with a library of information about countless extinct and existing civilizations. Perhaps the universe is already filled with such transmissions, crossing the cosmic voids, carrying the hopes and dreams and knowledge of civilizations that died before our sun was born. We have only recently gained the ability to detect such signals, and we have only been seriously looking for a few decades. The search for extraterrestrial intelligence, or SETI, listens for artificial radio signals from other stars. So far, they have found nothing definitive, but the search space is vast. There are billions of stars, countless possible frequencies, and we can only listen to a tiny fraction at any given time. The absence of detected signals might mean nothing. It might simply mean we have not looked in the right place at the right time, at the right frequency. Some scientists have proposed that advanced civilizations might use more exotic forms of communication. Perhaps they manipulate the cosmic microwave background itself, encoding information in temperature fluctuations too subtle for us to detect with current technology. Perhaps they use neutrinos, nearly massless particles that pass through matter almost without interacting, as a communication medium. Neutrinos could carry signals through the densest obstacles, straight through planets or stars, something radio waves cannot do. Or perhaps they use quantum entanglement in ways we do not yet understand to communicate instantaneously across any distance. We do not know what is possible with truly advanced technology. The question of whether we will ever leave the Milky Way is intimately connected with the question of what we will become. If we remain biological humans with lifespans measured in decades, then the answer is almost certainly no. The time scales are too long, the distances too vast. But if we transform ourselves, whether through genetic engineering, cybernetic enhancement, mind uploading, or merger with artificial intelligence, then the possibilities change. A being that lives for millions of years would experience an intergalactic journey very differently than we would. A digital consciousness that can be copied and backed up might be willing to take risks that biological humans would never accept. An artificial intelligence that thinks 1,000,000 times faster than humans might experience a 1,000,000-year journey as only a year of subjective time. These possibilities sound like science fiction, and indeed, much of our thinking about the far future is inspired by science fiction. But science fiction has a remarkable track record of anticipating real developments, even if the details are often wrong. Jules Verne wrote about submarines and space travel decades before they became real. Arthur C. Clarke envisioned communication satellites in geostationary orbit years before they were launched. Science fiction helps us think about possibilities that current science cannot yet confirm or deny. It expands our imagination and helps us ask better questions. One of the most thought-provoking ideas in science fiction is the concept of the technological singularity, a point where artificial intelligence becomes capable of recursive self-improvement, rapidly advancing far beyond human intelligence. Once A, I can design better AI. Those better AIs can design even better ones. And the pace of progress might accelerate exponentially. The result could be an intelligence explosion, leading to superintelligent AI. That is to us as we are to insects. Such an intelligence would have capabilities we cannot predict or imagine. It might solve problems we consider impossible. It might develop physics we have not dreamed of. It might make intergalactic travel trivial. The concept of the singularity is controversial. Some researchers think it is inevitable and imminent, perhaps arriving within this century. Others think it is impossible, or at least far more distant. Many worry about whether such an AI would be friendly to humanity, or whether it would pursue goals orthogonal or opposed to our survival. This is the AI alignment problem, ensuring that artificial intelligence remains aligned with human values, even as it becomes more capable. It is not obvious that this is solvable, and the stakes could not be higher. If we create superintelligent AI, and it is aligned with our values, it could be our greatest achievement, a partner in exploring and understanding the universe. If it is not aligned, it could be our last invention, terminating human existence or transforming us into something unrecognizable. Either way, it would fundamentally change what it means to be human and what our future might hold. An aligned, superintelligent AI. I might consider the question of intergalactic travel and solve it in ways we cannot currently foresee. But perhaps we are getting ahead of ourselves. Before we worry about leaving the galaxy, we should ensure we survive long enough to contemplate it seriously. Humanity faces numerous near-term existential risks. Climate change is altering our planet's atmosphere and ecosystems in ways that could make large regions uninhabitable and trigger social collapse. Nuclear weapons could devastate civilization if they are ever used in large numbers. Engineered pandemics could spread globally before we can contain them. Asteroid impacts, while rare, could cause extinction-level events. The development of powerful technologies without adequate wisdom to use them responsibly creates risks we are only beginning to understand. If we can navigate these challenges, if we can develop the maturity and wisdom to match our technological power, then we have a future measured not in decades or centuries, but in billions of years. We have time to dream of galaxies. We have time to develop the technologies that make those dreams real. We have time to become something greater than we currently are. The question of whether we will ever leave the Milky Way thus becomes less a question of physics and more a question of whether we will survive long enough and remain ambitious enough to try. The universe is indifferent to our existence. It will continue expanding. Stars will continue to form and die. Galaxies will continue to merge, whether we are here or not. But if we are here, if we persist, if we grow, then perhaps someday our descendants will look back at us from another galaxy and wonder what we would have thought of their achievement. They might remember us as the first generation to seriously contemplate intergalactic travel, even if we never achieved it ourselves. They might honor us for keeping the flame of curiosity alive, for asking the big questions even when the answers seemed impossibly distant. Or they might not remember us at all, separated by such vast gulfs of time and transformation that we would be as incomprehensible to them as they would be to us. There is something both humbling and inspiring about these thoughts. We are connected to the cosmos in ways both literal and metaphorical. The atoms in our bodies came from exploding stars. The molecules of water we drink have been part of countless other beings throughout Earth's history. We are temporary arrangements of matter and energy, brief patterns in the flow of entropy. Yet we can think, we can wonder, we can reach for the stars. Perhaps that reaching is what defines us most fundamentally. Humans have always been explorers, pushing beyond the familiar into the unknown. We crossed oceans in fragile boats, not knowing what we would find. We climbed mountains because they were there. We went to the moon not because it was easy, but because it was hard. This drive to explore, to understand, to push boundaries is deeply embedded in our nature. It has served us well, carrying us from the African savanna to every corner of the earth and beyond. As we look out at the Milky Way and wonder whether we will ever leave it, we are exercising that same drive. We may never personally travel to another galaxy. Our children or even our grandchildren's grandchildren may never do so. But by asking the question, by thinking about what it would take, by dreaming of those distant islands of stars, we are doing what humans do best. We are reaching for something greater than ourselves, something that extends beyond our individual lives, into a future we can barely imagine, but fervently hope to help create. The night sky invites us to dream these dreams. When we look up and see the faint band of the Milky Way stretching across the darkness, we are seeing our home galaxy from within. Those countless stars, those vast clouds of gas and dust, all of it bound together by gravity into a magnificent spiral structure, rotating slowly through space. And beyond it, separated by voids of nearly empty space, lie other galaxies, other islands of stars, each potentially home to their own worlds and perhaps their own civilizations, asking the same questions we are asking. We do not know if we will ever reach them, but we know that we can wonder about them. We know that we can study them, calculate the distances, imagine the journeys, develop the theories that might someday make those journeys possible. And that, in itself, is remarkable. The universe has become aware of itself through us, and through that awareness, it contemplates its own vastness, its own mysteries, its own possibilities. Whether we ever leave the Milky Way or not, the fact that we can ask the question reveals something profound about what we are and what we might become.